Here is an example of an NMR spectrum that I pulled off the internet. It's from New Mexico State University. So, a lot of times you'll get the formula of the molecule and you want to figure out what that molecule looks like. And when you look at the formula, the first thing you want to figure out is how many degrees of unsaturation are there. And we know that in a saturated molecule, there will be 2 more than twice as many hydrogens as there are carbons. So in this case, N is 6. 2 times 6 plus 2 is 14. So if this molecule were saturated, we would expect there to be 14 hydrogens, but there's only 10. For every 2 hydrogens that we're missing, there's 1 degree of unsaturation. So to figure out the actual degrees of unsaturation, we find the number of hydrogens that we're missing and divide by 2. So this is 4 divided by 2, or 2. So that means in this molecule there are 2 double bonds, or 2 rings, or 1 double bond and a ring. And so one question we might ask is, are there double bonds between carbons and oxygens? What kind of functional group is in this molecule? And to answer that question, oftentimes we look at an IR spectrum. So let's say that we did look at an IR spectrum, and it doesn't have a big band between 1600 and 1800 wave numbers. And what that tells us is that there's no carbonyl group. So we're likely looking at carbon-carbon double bonds or a ring. So what we have to do is look at the shifts and the splitting. And this is a very handy table to refer to. This is table 14.1 in your book. It's called Approximate Values of Chemical Shifts for HNMR. And I'm going to draw your attention first to this these methyl hydrogens here, which have an approximate chemical shift of 0.9. Now this big signal is exactly at 0.9. So it's a good bet that this corresponds to methyl protons. Another indication that this is true is that there are 6 protons that are responsible for this signal. You can tell from this integration line. So the more this line goes up, the stronger the signal and the more protons are responsible for making it. But anyway, the fact that there are 6 hydrogens responsible for this signal indicates to me that there are 2 symmetrical methyl groups that are giving this signal. So let's assume that they're bonded to the same thing. The next thing we can figure out is how many hydrogens are on the carbon that both of these methyls are bonded to. And we know it's 1 because this signal from the methyls is split once. If there's a doublet, that means there's only 1 hydrogen that is doing the splitting. The rule of thumb to remember is that the number of peaks is 1 more than the number of hydrogens within 3 bonds of the protons that are responsible for the signal. So for this doublet peak here, these 6 hydrogens are responsible for the signal, and since there are 2 peaks, there's only 1 hydrogen that's splitting them. So we are assuming that our methyls are connected to a CH, or a methine group. Let's find out where that signal would be. On our table, here's the methine proton, and it should be about 1.4. And here's a signal in our NMR spectrum at about 1.4. Well, it's more downfield than 1.4. But I think this is This is the signal from this hydrogen, and I'll tell you why. First, look at the integration line. It's very shallow. There's only one hydrogen that is giving this signal, and that's what we are expecting here from this methine proton. The second reason I think this signal is from this proton is that it is split like crazy. And we know that if indeed we are correct about the first part of our molecule over here, this proton signal is going to get split by all of these 6 hydrogens at least, plus from whatever's over here. So they have blown up this this signal here, so we can see in great detail each of these little peaks, and it looks like there's 9 of them. We got the tiny little thing over here, 1, 2, 3, 4, 5, 6, 7, 8, and the tiny thing over here makes 9. So this hydrogen must have 1 less hydrogen neighbors within 3 bonds. So if there's 9 peaks, there must be 8 hydrogens within 3 bonds. And we've already accounted for 6 of them, so if we make this a CH2 over here, that would be 2 more, and that would make the 8 that we're looking for. So if it's true that we have a CH2 over here, we should see a signal that has 2 hydrogens. Here's one. This integration line shows 2 hydrogens. And the interesting thing about this signal is that it's very downfield. It's way on the left over here at about 3.4 ppm. And we were expecting something like this because the oxygen in this molecule is probably in an ether functional group, or maybe an alcohol. And in an ether functional group, because the oxygen is electronegative, it's pulling electrons away from the neighboring carbons and hydrogens, and it's de-shielding those hydrogens, pulling the signal downfield. In our table, we have ether hydrogens here, and they should show up at about 3.3, which is almost exactly where we're looking. So I think it's a pretty safe bet to say that the carbon that is bonded to the hydrogens that are responsible for this signal is single bonded to an oxygen, and that oxygen is what's responsible for pulling this signal all the way down to 3.4. So to review, we've accounted for 3 out of our 4 signals. We decided the one upfield was the methyls. This one that's super split up is from the methine. And we only have 1 more signal to account for, but 2 carbons. And both degrees of unsaturation. But only 1 hydrogen. So we have a lot of pieces that have to fit together in this last part of our mystery. So I'm going to ask myself, what kind of proton could possibly be responsible for a signal at about 2.5 or 2.6? And this table can tell us, I don't know if you can see, but this is an alkyne, an external alkyne. With 1 hydrogen that should give a signal of about 2.4. So let's say that this signal is from an external alkyne. Does the splitting pattern make sense? Yes, this peak is not split at all. We have a single peak, so we know that the hydrogen that's responsible for it is isolated. And if it were an internal or an external alkyne, it would be isolated because there are no hydrogens bonded to this carbon. And if it were an external alkyne in this molecule, that would take care of both our degrees of unsaturation because there's 2 additional bonds in here. So this would actually make all of the puzzle pieces fall together. I'm going to tentatively complete our molecule and then double check to make sure everything makes sense. Remember when we were looking at the expected shift of the methine group and we expected 1.4 and it's actually pulled to about 1.7 or 1.8? Well, now we can explain that since we see this molecule. The methine group here is close to this oxygen. So this oxygen is pulling electrons from the methine region through the inductive effect. And that is pulling the methine signal a little bit slightly more downfield than we'd expect to normally see it. And the same thing's going on with our triple bond hydrogen over here. The table says we'd expect to see it at about 2.4, and we see it a little more downfield at about 2.6. And again, that's because this hydrogen is somewhat close to this oxygen, which is pulling electrons in inductively and pulling the signal a little bit more downfield than it otherwise would have been. And it looks like all the splitting is as we'd expect it to be. For example, this methylene here is split once, it's a doublet, and it's in our molecule that makes sense because it's only near one other hydrogen that would split it. So when I look at this, all of the signals from our hydrogens are where we'd expect them to be, and all the splitting is how we'd expect it to be if the NMR spectrum was from this molecule. So I feel pretty confident that we've solved this NMR.
Made with Doodlecast Pro.